All right, everyone, we're gonna get started here today, right now. Oh, my iPad's being a little fucking asshole again. Okay, so let's see if restarting it will fix it. So while I'm kind of fiddling with that, just a quick update of everything that's going on right now. So assignment 6 was due last night. Gradescope is open until Wednesday, so if you still need to submit, you can. Yeah, that's assignment 6. That's going to be a big programming assignment, and so now we're, got a pretty good idea of where we stand in the course. We're gonna have basically this week, we're gonna be doing Unit 6. Next week, we'll be doing Unit 6, and then the week after, we'll be having our second exam. So it's 2 weeks of a new unit, and then a week of review, and then exam. So our second exam is gonna be on November 13th, which is a Thursday, and the Tuesday of that week, November 11th, we're going to have a review session in this classroom. So, a couple of points just about that really quick. The exam is going to be on the 13th. It'll be open all day. It will be the same basic format as the first exam. We'll talk about it more as we get closer to it. And that's really the main thing I wanted to say. The study guide for exam 2 is already made available if you want to review it. It's on Canvas under the exams module, and it will include pretty much everything since our last exam, so units 4, 5, and 6, which means this material. So I just want to give everyone a heads up that that's what we're going to be doing going forward. And I also want to let everybody know that next week we only meet on Thursday. Next Tuesday we do not have class because it is election day. So please go vote and tell your friends to go vote. I like having rights. It would be really nice if that continued. So, and I really wish I was being bombastic about that. I'm not. So please go vote, and if you would like extra credit for voting, well, then just let me know you voted. Just send me that little email. You can vote early, and that if early voting is still going on, you can vote in person the day of. If you are not registered to vote, I'm not sure voter registration, it might still trickle into this week, but you can register on election day and vote with a provincial ballot, which is something I'll accept and count. So again, your voting evidence, please do not show me who you voted for, just the idea that you went and did a democracy. That's all I'm looking for. So, so we do not have class next Tuesday because of election day. So that's real close, which is nice. And I'm going to just say in the YouTube, if you're following along on the YouTube chat, I'm hoping that the screen lasts. I'm skeptical. I feel it's just kind of decided, oh, well, it says it's working, so we'll see. We'll see if it behaves today. But yeah, okay, so that's going to be everything. Just we have Unit 6, and then Exam 2 is going to be on November 13th. And just a heads up, by the way, that Exam 2, we are certainly going to have some stuff from Unit 6 that you'll have a homework on that won't be graded by the time we take the exam. So please do take the opportunity during our Exam 2 review session to ask any questions you might have about any material, but specifically this stuff. We have a homework related to Unit 6, and if there are questions about that material, the review session, I think, is a great time to ask it so that you know for sure what's going on before the exam. Yeah, I apologize that grading has been a bit slow this semester, but we at least have that so that it's not, a complete wash, as it were. Okay. So, let us start a brand new unit, leaving the functional paradigm long behind us, thank God, and just jump right in to context-free grammars and lexical structures. Okay? Now, for those of you who have taken 303 already or are taking 303, context-free grammars are going to be familiar to you, maybe in a scary way. We are doing context-free grammars, and I am going to kind of introduce them from the top. It's not a guarantee you've taken 303 when you've been in here, but 303's focus on context-free grammars is a lot deeper, it's a lot more mathematical, it's a lot more fleshed out. We are using context-free grammars as a tool to get to an endpoint, and so we're really only going to engage with these context-free grammars as much as we need to for the usefulness of the tool. But this will make more sense in a minute. So, to start off, I want to talk about what this unit is really about, and that is the syntax and semantics of a programming language, of programming languages, if you will. Basically, the syntax is defined as the form or structure of the expressions, statements, and program units, whereas semantics are the meaning of the expressions, statements, and program units. Syntax and semantics combined provide the overall language's definition. So a language is effectively defined by the rules which specify valid structure, or syntax, and valid meaning, or semantics. So again, syntax, think structure; semantics, think meaning. Now, we've been talking for a while, right? This is programming languages, but we've been focusing on a specific programming paradigm for the past couple of weeks. And then before that, we were talking about Python. And then before that, yes, it was the environment, but it was also a lot of conversation about C. Here, we are going back to generalized computer programming language theory. Syntax and semantics, we're not looking at a specific language necessarily. Some examples will use C code because that's just a lingua franca for code examples, but these basic principles are universal to high-level programming languages. Just want to start with that. So, if syntax and semantics make up a language's definition, well, who cares? Why do we care how our language is defined? Well, if we are designing a programming language, we're probably going to care about, how our language is in fact defined and designed. If you are designing a compiler, then you really need to know the valid structure and meaning of all program statements. If you're compiling a piece of code, if you're translating a piece of code to machine language, then you need to be able to verify that the code being translated is valid. That's, quite important, right? We don't want to attempt to translate nonsense into a different language and just see what comes out, right? If you have an English paper, which is just incoherent, right? Chat was having a bad day, and just the sentences don't make sense, the structure is not remotely valid English structure, and the meaning is incomprehensible to any English speaker. And then you just run that through a translation program to another language, say French or Spanish. What's going to come out the other side is also going to be incoherent, right? And if you're designing a compiler/translator, that's really bad. You want to be able to understand the structure and meaning of a programming language well enough that if someone provides you with a structurally inaccurate program, you can reject it and say why. If somebody tries to write code that maybe has valid structure, but the attempted meaning is not something the language supports or allows, then you want to be able to reject that program instead of just translating it to machine code and seeing what happens. So there's a lot of value in understanding the structure and meaning of a language as defined by its implementers. And even if you're not designing a compiler, if you are just a programmer, a user of a programming language, well, maybe you don't need to know the structure and meaning quite as in depth as if you're designing a compiler or a language straight up, but all the same, the more understanding you have of the structure of your language, what is valid, what is invalid, what meanings work, what meanings are not acceptable, the more effectively you can utilize this language, the more effectively you can understand code written by others in that same language. So even if maybe you as a general programmer don't need quite the level of depth as a language designer, understanding the syntax and semantics of your language makes you better writing code in that language and maintaining code in that language. And again, if we think about gigs in industry, 90% of what your work's gonna be is maintaining other people's code. And so, this has a lot of value to it. So, this unit is going to cover the structure in terms of syntax and the semantics in terms of meaning of a programming language. We are primarily going to focus on the syntax or the structure. All right, we'll talk about semantics a little bit, but primarily we're going to focus on the syntax, which is where we're going to start. So, what is the syntax? Well, again, the syntax is the structure of a programming language. So it's the allowed order of words, the allowed types of words, basically the way you can arrange tokens in an order that is or is not allowed. So how do we specify what is and is not valid syntax, right? How do we create this? Well, one option here is just a written document. You know, for example, I could describe an if statement in C by saying an if statement consists of the keyword if, followed by an expression inside a parentheses, followed by a statement, followed by an optional else part consisting of the word else and another statement. So, this sucks. This is fucking awful. So first off, I need to know what a statement means. I need to know what an expression means. And that's not particularly obvious or intuitive. Even still, right? That's just the language we're dealing with here. But I want to kind of attack this on a deeper structural level. It's not that this isn't written well. It is. The issue is that it's written at all. This is a natural language description of the structure of a programming language. And natural language descriptions are not great. One of the key tenets of a programming language, something that we've seen since we started programming, is a lack of ambiguity. How things in programming need to be unambiguous. Computer systems do not handle ambiguity well at all. They really can't do anything with it. Natural language, on the other hand, is deeply ambiguous in a lot of ways. What a sentence or a set of sentences means to one person can mean something else to another. We attempt to have a, solid understanding, a collective shared understanding among communities and groups, but at the same time, we struggle with that, right? Different dialects, different ways of speaking, different interpretations of the same words. It turns out that natural language is just not very good at describing programmatic concepts because programmatic concepts have to be unambiguous, and natural language is definitionally ambiguous. Particularly English, by the way. In part, the lingua franca of diplomacy, yes, World War II, but also because it's a language where you're quite capable at saying a lot of words without really meaning much of anything. Former Secretary of State John Kerry was kind of a master at this. You could give an hour speech and effectively say nothing. Now, if you're trying to be a diplomat, that might be to your benefit. If you're trying to define the unambiguous syntax of a programming language, a touch less so. And so not only is it open to interpretation, it's also wordy as all hell, and it's verbose, and it's not something I really think any of us want to engage with. And then to add on top of that, this is just English, right? It's a specific natural language, and not everybody speaks this. And if you have to go translate this to another language, well, it's not perfectly unambiguous. So that translation can introduce issues or flaws. So, when you translate a single text through different languages over and over, what comes out the other end, it's effectively a big old game of telephone, and it might end up meaning something completely different. The Tower of Babel project, this was a long time ago, but, an eternity ago on the internet, there was a goofy little program that would basically just run some text through Google Translate a few times through different languages and then spit it out the other end. And it was just always incoherent. And I'm sure Google translates a lot better now, but almost definitionally, when you do a lot of natural language translations, it's really easy to change the underlying meaning. So if you're writing, the syntax of the C programming language in English, and somebody who does not speak English wants to code in C, this might constitute a problem. And that is just another reason why natural language is really not the juice when it comes to describing the structure of a programming language. Right? Not to mention that the definitions of words don't only change based on culture, don't only change when you translate from one natural language to the other, time also plays a factor. Try reading Beowulf. Try reading, the Chaucer tales or whatever the hell. It's not comprehensible. It's Old and Middle English, and it's actually unrecognizable. Well, more or less, to modern English readers. Hell, Shakespeare is pretty dense and difficult to get through because people don't talk like that anymore. Shakespeare invented hundreds of words that are still in modern use, but if you just go read it in the whole iambic pentameter-ass glory, it makes a lot less sense. You gotta kind of sit and read through it. And even then, you're missing double and triple entendres that Shakespeare is making jokes about. And I'm not an English person in that way, but just, I've watched enough video essays, right? And so, time also plays a factor. C was developed in 1972. It is 2025. C is not going anywhere. It is going to be with us. Well, provided people continue forward, provided our collective societies don't crumble to dust, it's going to be with us until that point. It's just not going anywhere. It is kind of ingrained itself fundamentally into our digital culture. And our digital culture underpins everything. So this is going to be with us for another 50 years. And it'd be really great if in another 50 years and another 50 after that, we could still understand what the hell the structure of this language was. Okay. I'm milking this a little bit, but all the same, I think this is A, interesting, and B, these type of challenges tend to not be discussed in terms of computer science, but yet they exist in this field as much as they do anyone else's. So, I have just been shit-talking natural language descriptions of syntactical structure for 5 to 10 minutes. So do we have an alternative? Yes, gracefully, I have set ourselves up for an alternative. So we have a different way of describing structure. So in 1950, Noam Chomsky, yes, that Noam Chomsky, he's a linguist by trade originally, go figure. So Noam Chomsky develops the idea of context-free grammars. A context-free grammar is a formal specification of syntax which consists of a series of grammar rules. So Chomsky develops this in 1950. He's thinking about natural language. All right? Now, John Backus and Peter Naur, developed a notational system for describing these grammars called Backus-Naur forms, or BNFs. So again, John Backus, our good old friend from IBM, the developer of the first high-level programming language Fortran, back at it again here in programming language history. So, context-free grammars and the use of BNF to describe a context-free grammar first shows up to describe the syntax of Algol 60, which, whatever, we don't talk about Algol 60 in here, but the 60 is because it was developed in 1960. So it's been kicking a while, right? Our first high-level languages come out in the 1950s, and before the, right at the turn of the next decade, we are using a BNF, context-free grammars, a structural system to describe the syntax of this language. So pretty much immediately, once we start seeing these tools, once these tools are developed, we put them to use. We see the benefits they bring us. So, really, we have original BNF and we have extended BNF or eBNF. I'm going to stick to talking about original BNF for now. We'll move on to extended when we get there. Don't worry about syntax diagrams. I don't really think we're going to talk about those. So, all right. I have some definitions, followed by some examples, followed by some more definitions, followed by some more examples. So that is how we're going to do this thing. So I'm going to kind of info dump a little bit. This is all about what a context-free grammar is, how it works, and then we're going to just apply it right away. I know this is really term heavy. So let's just jump in. So we'll formally define a context-free grammar as a formal specification of syntax which consists of a series of grammar rules. Metasymbols are symbols used to describe the grammar rules. For our purposes, there are two major metasymbols for BNF, the arrow and the pipe. And the straight line is traditionally just called a pipe. So the arrow is a metasymbol that can have the form or goes to. I often will refer to it as like decompose or breaks down into. That's the basic rule, right? It's indicating a transformation of some kind. The pipe metasymbol indicates a choice. Similar to how two pipes is the OR operator in C and C-influenced languages, a single pipe in BNF is the OR operator, effectively. So each rule has a single non-terminal on the left, an arrow metasymbol, followed by a sequence of terminals and non-terminals on the right. A non-terminal okay. A terminal, let's just start there. A terminal is a word or token symbol that cannot be broken down into subparts, right? So a terminal, right, a terminator, right, the end of the line, a terminal cannot be broken down, whereas a non-terminal can be. And how a non-terminal breaks down is defined by a specific grammar rule. So let's just take a look at this. So here we have our simple grammar here. Now we have our start non-terminal. Rule number 1, we see that a sentence breaks down into, indicated by the arrow, a noun phrase, a verb phrase, and a period. Now the period is a terminal. It's just the period character. It's just a single character on its lonesome. A noun phrase and a verb phrase, these are both non-terminals. Because a noun phrase, well, this breaks down into subparts. What subparts? That's defined by rule number 2 of our grammar, right? The noun phrase non-terminal is defined as breaking down into an article non-terminal and a noun non-terminal, one after the other. What's an article? Well, an article breaks down, as defined by rule 3, into either the a terminal or the terminal. So an article is just one of two strings, effectively. All right? Now, again, this is a very simple grammar. There's not a lot of valid structure options here. That's okay. And a noun breaks down to girl or dog. A verb phrase breaks down to a verb, then a noun phrase, and a verb breaks down into C's or pets. So what we're seeing here is that in order to be syntactically valid or structurally valid, a sentence would have to follow this structure as defined by the grammar. So in this simple grammar, which is a very small subset of English, a noun phrase, all sentences start with a noun phrase and then go into a verb phrase and then have a period. So in order to be considered a sentence, you have to have a noun phrase, then a verb phrase, then a period. What's a noun phrase? Well, it's an article, then a noun. What's an article or a noun? They're defined later in the grammar. So we can use this to establish if any sentence is structurally valid or invalid for this BNF grammar. Okay? And again, using just, English phrases is a little goofy, but that's fine. It's defining a structure. That's what matters. Rules 2 through 6 describe the structure of noun phrases, verb phrases, and all the other non-terminals. And the non-terminals on the left-hand side are being described by the sequence of items on the right. Right. Each grammar rule basically defines how a non-terminal breaks down. So every non-terminal used in the grammar has to have its own grammar rule that defines how it works. Okay? So, sometimes grammar rules are referred to as productions. I don't really care about that. Sometimes notations use angled brackets to indicate a meta symbol. You won't see that in here, so that's the goofy way, not goofy, that's the way we're not using. It's common other places, just here for completionism. Really the main thing is that we will sometimes see double quotes being used to differentiate between a meta symbol and a terminal. Because like one of the problems with our grammar right here, right now we only explicitly define two meta symbols, so it's like okay. But we have this little period here, which is just a single character terminal. And it's like worth asking, is that a terminal value and part of the grammar, or is that a meta symbol which is describing how the grammar works or behaves, right? The pipe indicates a choice. The arrow is telling us that the non-terminal on the left breaks down into these subsequent parts, right? The meta symbols tell us information about the grammar, and the terminals are just part of the grammar. And so is the period a meta symbol or just a terminal? Now, again, here we only have two defined meta symbols, so that's an easy answer. But as we add more meta symbols and the complexity increases, we may start double quoting our terminal values to just separate them from our meta symbols. So, the last little blob of language that we're going to define before a real example is these guys. So, a context-free grammar shows us how to generate syntactically or structurally valid strings of terminals. So, a couple of things we can do with these. A derivation is the process of generating a syntactically valid string of terminals by beginning with a start symbol and replacing left-hand sides by choices of right-hand sides in the rules. A derivation is basically taking a start symbol and seeing if we can break it down in a way where the resulting list of terminals matches some input, thereby validating that our input is syntactically or structurally valid for the given grammar. A start symbol is just a non-terminal representing the entire top-level phrase being defined, such as sentence or program or function. And the language of the grammar is a set of all strings of terminals for which there exists a derivation beginning with the start symbol and ending with a string of terminals. So, this is very fancy definitions. It's not as bad as it might sound. So, we have a grammar for a small language here. This is like a very overly simplified little programming language. We have our start symbol as program. Program breaks down to the begin terminal, statement list non-terminal, and then end terminal. Statement list statement breaks down expressions and vars. So we've got 5 non-terminals. We describe how they break down. And now we are basically asking to do a leftmost derivation of begin A equals B plus C semicolon B equals C end. Basically, what we're asking when we say do a leftmost derivation, because it's, fancy math language, right? What we're really just asking is, hey, is this statement, this program, a valid structurally valid for the given grammar? If these 5 grammar rules define a set of valid programs, then is this begin A equals B plus C, B equals C end, is that a valid program for this language? That's the question being asked. So let's try and find out. So I am going to spare us the iPad nonsense. I've gotten better at just typing everything in a text editor, so we're going to keep going with that. And I'm going to try not to botch it. Okay, so I'm going to do 2 things. 1, I'm going to bring this guy up here. And then 2, oh, scary. That's not an image. That is just a gray background. Okay. All right, and then maybe put it down here so it doesn't just get blocked by my face. Yeah, this will work. Okay, so basically, we want to see if we can end up with this result. We basically know our end point, and we're trying to start with the start symbol and break it down into this. That's the goal. So it's a leftmost derivation. So whenever we do a derivation like this, a validation like this, the first thing we do is we always start with the start symbol. So basically we say the first thing we have is a program, because that is rule number 1 here. Now what does a program break down into? Well, a program breaks down into the begin terminal, the statement list non-terminal, and then the end terminal. Yeah, because, I'm going to just put my terminals in quotes just to differentiate them from my non-terminals. Strictly speaking, we don't have to do this. We'll use context, but just to be extra clear. So basically, what I have here is we say program breaks down into a begin, then a statement list, then the end symbol. Now, we then need to break down statement list. Why statement list? Well, because begin's a terminal and it doesn't break down. And then if we're doing a leftmost derivation, well, that means we just start with the leftmost symbol and go left to right. So we know a program, which is our start symbol, breaks down, as defined by the BNF, into a terminal, a non-terminal, and then a terminal. This terminal cannot be broken down. This non-terminal can be. So that's exactly what we're going to do. We're going to do a substitution, and that's going to be the next line of our derivation. So a program breaks down to begin. Now a statement list breaks down. So basically, what do we replace statement list with? Now, rule number 2 says a statement list breaks down to a statement or a statement, a semicolon, and then a statement list, a second one. So which one do we want? Now, we're going to kind of see that if we want to do this programmatically, this is a more persnickety thing to answer, but we're not doing it programmatically. We're doing it with our, human brains, so we can cheat a little bit. This is what I want my end to look up like. This is what I want my end result to be. I see a semicolon in here. There's an option to break down statement list into something with a semicolon terminal. None of the other rules have a semicolon in them. So I'm going to just assume that I'm going to have to pick the option, this option, as to what to break statement list down into. So I'm going to say that a statement list breaks down, in this case, into a statement, a semicolon, and a statement list, and then we have the end terminal. So that's, again, how we do this. We take our leftmost non-terminal, find the associated grammar rule, and break it down into the subsequent parts that it's made up of. Now, when we have an option, for now, we just need to look at the target end goal we want to get to and use that to figure out which choice we want to make. We'll figure out maybe less hacky ways to do this as we dive deeper into this material. But for now, let's just keep going down. So our second line of our derivation, we have a terminal and then a non-terminal, and it's a leftmost derivation. So we take the leftmost non-terminal and we break that guy down. So I'm going to just do that. A statement breaks down to a var equals expression. So my next line is going to simply take statement and replace it with var equals expression. And we still have our semicolon, our statement list, and our end symbol, right? All of that's still right there. But we have swapped out statement for what statement breaks down into. And now our leftmost symbol is the var symbol. So That's what we'll swap out next. So what does var break down into? A or B or C. Which one do we want? Well, I once again say let's look at what we're aiming to generate. The first terminal here is begin, which we already have. The second terminal here is A, so we would really want this to be A, right? Because we are trying to get this derivation to ultimately match, when it's done, the list of terminals we started with, right? Because if it does that, then we validate it, that we can have a program non-terminal break down into this, meaning that this guy is a valid program for this grammar, for this language, right? We want to prove that this is a structurally valid program, so we start with the program non-terminal, and we keep breaking it down, and if this input is valid, we should be able to break a program down into exactly this output, okay? So we are starting at the beginning and then aiming for a specific output, so we are guiding our derivation, but again, that's okay, that's the point. Right? If we can start from the program non-terminal and get to this endpoint, that validates that this endpoint is a valid program in this grammar. And that's what we're trying to prove. So I'm going to keep going. Program breaks down into begin, A, equals, and then expression. Now an expression breaks down to a var plus var or a var minus var or just a single var. Once again, I look up at this guy. This guy is B plus C, so I'm going to assume that my expression needs to be var plus var. So, copy, paste, and then we swap out expression with var plus var. And now we need to replace the leftmost var, this guy, with B, which is what I'm going to do. And then the next symbol, this var, we replace that with C. Okay. So now, a program breaks down to begin, A equals B plus C semicolon. It's matching everything so far, looking good. And now we've got another statement list. A statement list breaks down to a statement or a statement semicolon statement list. I already have my one semicolon here. There isn't a second one, so I'm assuming statement list needs to be broken down, whoopsies, into just a statement. A statement then is broken down into a var equals expression. Oh, hush. And I will pull you up here, pull you down here, see if we can make it work. So now the leftmost terminal is a var. So a var will swap out. We want B, and var can, B is one of our three options for var, so we can make that swap. And then the next thing we have, the leftmost terminal after that substitution is expression. So what do we replace expression with? Well, expression is var plus var, or var minus var, or just a solo var. We have B equals C up here, so I think we just want the solo var because we're just trying to get B equals C, not B equals C plus or B minus, just B equals C. So if I make this var, and then the next derivation, we replace bar with its, terminal value C, well, then we're done. Because we only have terminals here. We don't have any non-terminals. And I don't need the parentheses. I really probably shouldn't have put them there because now the homeworks are going to have them. But I can't bold anything on this basic text editor. So this is what our program ultimately derives down into. If I just delete you, you won't scroll. So we see that we can start with a program, break down program into its subsequent component parts, and then just swap out the leftmost non-terminal for its component parts, repeat this process until all non-terminals are gone, and we are kind of directing our derivation, but we are able to start with the program non-terminal, the start symbol, and break that down into the sequence of terminals, begin A equals B plus C, semicolon B equals C end, which is exactly what we were looking for. So that tells us that this guy is a valid program in the given grammar. And that is the value of BNF, all right? Now, doing the actual derivations, you will have to do this once or twice. You'll have to do it on a homework. You may have to do it on an exam. The principle, I think, I will make sure they're not too annoying and tedious. The homework might be a little, if it showed up on like an exam, it certainly wouldn't be. I'll also say that I was copying and pasting, so it was pretty trivial, but you'll see this a lot of the time. You won't see the start symbol necessarily repeated until the very end. A lot of times it's implied because it's not changing. A lot of times you'll see it written kind of like this, where the start symbol is provided at the beginning, and then if you're handwriting it, you just don't do, this is acceptable. Just put the original start symbol back at the end. The start symbol doesn't change. It can be inferred. Okay? But yeah, so that's the idea here. That is a derivation, and again, we're using this to validate if a specific set of terminals is valid structurally for a given grammar. So, with all that kind of being said, any questions about this leftmost derivation that I just did? Yeah.
We don't need commas or the quotes on anything.
Yeah, that's right. We don't need the quotes on like anything. I just use them to differentiate between the non-terminals and terminals. Sometimes you'll see them bolded. You'll see them in the grammar a lot of the time, but when you're doing your own derivations, you don't need them, and when you get to the end, you really shouldn't have them, right? So yeah, you'll see terminals quoted in the grammar just to separate them from meta symbols, but like you don't need them when you're doing your derivations, just as long as you can keep everything straight. All right, but thank you, that's important. Yeah. And you can see that in the example I provide for the lecture slides. There's no quotes on any of this. I was just kind of winging it and felt like doing it that way. So, yeah, whatever. So this grammar, overall, that we were just working with, it's got 9 terminals within the grammar. Begin, end, the semicolon, the equal sign, the plus sign, the minus sign, then A, B, and C as capitals. We only define 9 terminals. There are 5 non-terminals and 5 grammar rules. Number of grammar rules should always match the number of terminals, at least in any grammar we're seeing in here. Now this language is infinite, actually. This is one of those places where infinity is weird. It's a very small subset of, there's not many things you can say, but it's infinite because of rule 2. Because a statement list can break down into a statement list, right? And so if a statement list can break down to a statement list, it could theoretically do this forever, an infinite number of times. So technically that makes this grammar infinite. Most BNFs are infinite. Some are finite. If there is a loop, it's almost certainly infinite. Finite grammars almost always do not have any ability to loop back to a previous grammar rule. If you have a grammar rule that breaks into a previous grammar rule, it's almost certainly infinite. It's not a 100% guarantee. Math is weird, but it's a pretty good guess, pretty good assessment. Because you'll see like a statement breaks down to an var and an expression, which are both like lower in the grammar rule set, right? So it's only going one way. But yeah. Okay. Look, this is a very mealy, wordy definition that I'll go through, but I'm not asking you to memorize the definition as much as the concept behind it. So this is a context-free grammar, meaning that non-terminals appear singly on the left-hand sides of grammar rules, which means that each non-terminal can be replaced by any right-hand side choice, no matter where the non-terminal might appear in the language. That's all fine and good. What I really care about is there is no context under which only certain replacements can occur. That's what matters. When I look at this grammar here, statement list breaks down to a statement or a statement semicolon statement list. There's no context that gives you one option is required or the other, right? Now, if you are trying to derive to a specific endpoint, you might pick which one you want, but if you're just trying to make any valid program, there's no external context that tells you which choice you have to make. And that's important, all right? Context-sensitive grammars are messy, and we don't want to fuck with them. So we'll deal with context sensitivity somewhere else, semantically, i.e. not here. You can have context-sensitive grammars, that's a thing, mathematically, but for a programming language, we want a context-free grammar. We want our grammar to not have the context of the program influence what is and is not valid structure. There are times where programming languages need context. For example, a classic use of context is variables must be declared before use. In Java and in C, this is a big deal. In Java, you have to declare a variable before you use it. That is a structural rule, but that is also a context-based rule, right? The context of whether this specific identifier has appeared or not. So rather than making our context-free grammars contextual and messy and way harder to work with, we're just going to say the context-free grammars don't worry about shit that requires context. We'll deal with that somewhere else. So for now, that's how I'm going to leave it, just kind of let that sit there, right? BNFs are meant to define context-free grammars where we can make a non-terminal substitution whenever we want, however we want, and anything that might require context, we'll deal with that with another tool somewhere else down the line. That's the idea. So when we're defining the structure of a programming language, we'll do so in a context-free way, which just makes things simpler for us. I don't really care too much about the formal math theory, but just a grammar is context-free when non-terminals appear singly on the left-hand side of grammar rules, i.e., when the format is non-terminal derives into stuff, and that's the case for all the grammar rules in the language, then it's context-free, right? Because we're just saying, hey, this non-terminal breaks down to this thing. It's not this non-terminal if this condition is true, not this non-terminal sometimes and this non-terminal other times. We're simply saying this guy breaks down into these things whenever that opportunity arises. No ifs, ands, or buts. No context changes this definition. Okay? So, yeah, a grammar for A to the N, B to the N. So S, start symbol, can derive into AB or ASB. And you can play, this is really more 303. I don't care as much, but just to kind of show, right, is AAABBB described by this grammar? Yes, it is, right? Here we're going to go backwards, right? We can, AB breaks down into S, ASB breaks down into just S, ASB breaks down into S. So if you just have the start symbol, you can get to AAABBB with this quirky little one-rule grammar. All right? But again, this is a lot more 303-esque. And the theory is important to understand, which is why it's on this lecture slide, right? Hey, if we have a non-terminal S, terminal, and it breaks down to terminal AB, or terminal A, non-terminal S, and terminal B, well, then that describes a repeating pattern of A's, and then a mirrored identical number of repeating B's after it. And this is infinite because we can have as many A's and B's as we want, but because of the structure of this, it's always going to be the same number of A's and B's on both sides, and it's always the A side and the B side. We can never have ABA, we can never have BAB, we can never have more A's than B's or vice versa. All right? What do I really want to say about this? Okay. Yeah, okay. No, it's doable. Okay. So, context-free grammars are the norm, the standard, for expressing programming languages, and it makes it a lot easier to write translators, right? Because this allows the parsing stage to be automated. We'll talk more about the parsing stage in a bit. But effectively, if we have a programmatic set of grammar rules that define non-terminals and how they break down into collections of terminals and non-terminals, these are a set of rules. And the derivation we just did was a pretty algorithmic process, right? One step after the next step after the next step. It's not too much of a leap to say and infer that the programmatic nature of these context-free grammars will allow for automation to occur. So we could write a program that implements a context-free grammar, and that program's job might be to validate if some input, some collection of text-based characters, creates a structurally valid input for the given language, or if it's invalid. And if you think about it, that's actually one of the core components of what your compiler does. Think of Java, think of compiling Java. If you make a syntax error, the compiler does not translate your code and tells you, at this line, you did this thing, which was syntactically invalid. It makes the program untranslatable. Please fix it. That's effectively what we're talking about when we say parsing. You're taking in just an arbitrary collection of characters, and then you are going to apply the context-free grammar rules to them to programmatically assess whether this big old collection of characters is structurally valid for the defined grammar. And I think tying that to the Java compiler shows how that process of structural validation is a core component of high-level language translation, especially when we're thinking compilers. All right, I want to give you that feedback of what's going on. Okay. I guess really all I want to say here is that this BNF guy, it's very recursive, right? Expression breaks down to an expression plus an expression, or an expression times an expression. So in order to get repetition, we're using recursion. I think we've had enough of that, but all the same, it shows up with BNF, okay? This is just another example. We can do a derivation in the number 2, 3, 4 using this simple grammar. It doesn't even really use expression. It's just numbers and digits break down into each other. Cool. Okay. But here's the one thing I really want to pull out from this. Digit breaks down to a 0 or a 1 or a 2 or a 3 or a 4. That's tedious and annoying, right? And then to boot, right, when we start thinking about strings, right, when we start thinking about character strings, actually defining all of the valid terminals in a grammar is kind of a nightmare. That's almost impossible. Think about just any modern programming language. Like if you think of a C-based identifier, the rules for C identifiers, which like Java steals this and a lot of other languages steal this, it's like any alphanumeric string so long as the start symbol is not numeric. That's a valid identifier, and I don't want to try and manually hard code the set of what is, if not outright infinite, damn close to, as a bunch of individual terminal values in my grammar. So we can define terminals using regular expressions. So we're going to use regex in here a little bit. All right? Now, I'm going to just do a crash course in regex. I'm not going to assume anyone knows what regex is. You probably have encountered it in one form or another, but all the same. I'm going to just break it down off the top. So regular expressions are descriptions of character patterns, and regular expressions have three basic operations: concatenation, repetition, and selection. Concatenation is done by sequencing the items without an explicit operation. Parentheses can be included to allow for groupings of operations, so we can combine things together. Repetition is indicated by an asterisk or a plus after the item to be repeated, and a choice or selection is indicated by the pipe in between items. So if we have something like parentheses A, pipe B, close parentheses, asterisk C, what we're basically saying is that there will be 0 or more repetitions of A or B. Okay? So we can have 0 or more A's or B's, and any combination of that will match this regex, so long as it's followed by a C. And that C always needs to be there. Okay? So those are the main three things you can do with regexes: concatenation, repetition, and choice or selection. Now, strings that could possibly match this little regex guy, right? A, B, A, B, A, A, C, that's fine. A, A, C, that's fine. B, A, B, B, C, that's fine. Just a straight C, just straight C. That works too, because the asterisk is 0 or more repetitions. So 0 repetitions, and there's no A, there's no B. Strings that don't match would be something like A, B, A. There's no trailing C, and this regex requires one, so this wouldn't match the regex. BAC, well, it's got a C in there, but that C's got to be the last character. There's no way for A to show up after it. That does not match the regex. Right? You can think of a regex like a function, a Boolean function. You define the regex, given a set of input characters, you get a true or false value out. It's true if the set of input characters matches the regular expression, right? If using that regular expression, you can get those characters. And if you can't, you get false. It doesn't match. Okay. So, I'm going to go through some more regex stuff. I will just say this about regex. You're not going to be asked to memorize regex symbols, really. You will basically just want to be familiar with, I'll bring it up in a minute, but basically, I'm going to go through these operations. If you recognize the regex for a C identifier and know what that means, you'll be good for like an exam. The homeworks, you might need to parse some regex stuff a little bit, but the homeworks, I'm also going to just link you to a regex website that you can just programmatically validate regexes and see if they match or don't match strings. The goal here is that, yes, understanding the internals, the structure of a regex makes them, a lot easier to understand and work with, but there's not a regex course. Do your best, validate it with the online web tools, and that'll be enough. Regexes can get very galaxy-brained very fast. Some of the unit tests in 255 use some crazy regex shit in the background, and I cannot make heads or tails of it, which is my fault, by the way. That is a fatal flaw of my own, but all the same. Regexes can get wild and out of control real fast. We will not do that in here, all right? We're going to use regexes. I'm not going to say they're simple, but we're not going to go crazy on regex. We're going to use them to get what we need out of them and not a drop more. So I'm going to try not to go too over the top with the regex stuff. So just so we have these, some basic regex notation on top of what we already had, all right? We have concatenation, repetition, choice. We also have square brackets with a hyphen, which indicates a range of characters, all right? A question mark indicates an optional item. A period is a wildcard, which just says any character can match. And an escape character just like in programming, if you need to use a meta symbol character as just a normal character, the backslash is there to escape it. So if you need to match a question mark character and you don't want that to be the meta symbol of optional, slash question mark will match a single question mark character. So, also, we talked about repetition, and that can be a trailing plus or asterisk. If it's a plus, it's 1 or more repetitions. If it's an asterisk, it's 0 or more repetitions. Okay. So, square bracket 0 through 9, closing bracket plus, indicates simple integer constants consisting of 1 or more digits between 0 and 9. So basically, any int will match this regex, right? 1 matches this regex, 10 matches this regex, 3,072,000,072 matches this regex, right? It is the set of all base 10 digits repeated 1 or more times. Okay. And then down here is a little goofier, but we can break it down. The first part's the same. It's the set of all base 10 digits repeated 1 or more times. But then we have this optional component. Within the parentheses, and the end of the parentheses has that question mark, meaning everything in the parentheses is optional. But within the parentheses, we have a backslash period, so not the meta symbol wildcard, but just the actual period character, the set of 0 through 9, repeating 1 or more times. So this is a real number regex. The front is the integer. The optional component is the decimal point, and then fractional component. So 10 matches this regex. 10.2 matches this regex. 2,000,000.3359 repeating matches this regex. 10 point nothing, not a 0, 10 point blank does not match this regex. If you're going to have the period, you're going to have 1 or more integer numbers after it. You can't just do 10.0, and that does fit the regex. Right? So, no. I don't feel this, I think we get the point. We can break this down, but yeah, 0 through 9, repeating 1 or more times. This is just some goofy exponentiation, right? Optional, either capital or lowercase e, plus or minus, right? And then 0 through 9. So just 42, 42e2, 42e, the negative 02. And it's just a weird, goofy way of writing exponentiation. And see what I mean about how this can get out of control fast? Now, this is why you have like the web tools. Because this, if you have, it's similar to Common Lisp, that like, if you are adding the spaces where you need to and you can look at the subcomponents, none of them are too bad on their own, but it's when you just kind of have all of it thrown into your face at once that you're just like, oh fuck, what's going on here? So when you do look at a nasty regex like this, because even if we don't in this class, you'll probably see them before you graduate, right? Regexes are similar to functional in that most people, well, they're a lot more popular than functional, but like they're used, but the converted realize the power regex truly has and tend to go all in on making really powerful regex. And the rest of us look at those regex and say, what the fuck is that? I cannot read this. What does this do? And if it does not work for something, you cry and hope that whoever wrote it still works here and they're willing to fix it, right? That's the vibe with regex. They're very powerful, they're not that bad to use, unless people start going all in on them, in which case they can be kind of hard to decipher. But again, take that deep breath, break it down subpart by subpart. It's each, I think, subcomponent's very manageable. It's just when they're all thrown at you at once, it can get overwhelming. So this is not something I'm going to make us derive ourselves, but this. A through Z lowercase, A through Z uppercase, underscore. So what we're basically saying is this is the set of all upper and lowercase letters and the underscore character. So any So, and this doesn't have any repetition. So this is saying the first character of our string has to be a letter or underscore, upper or lowercase. The second set of square brackets is lowercase letters, uppercase letters, the digits 0 through 9, and the underscore repeated 0 or more times. This regex is C identifiers. So in C, any valid identifier is one where the first character is an underscore or an alphabetic character, and then as long as that first character is an alphabetic character / underscore, you can have just it be a single character identifier, or it can be as many characters as you want, and they can be numeric characters as well. So this is defining an alphanumeric string with an undefined max size. It can be as big as you want, so long as the first character is alphabetic or an underscore and not numeric. Okay? This, I'm not going to say literally memorize this, but like this is the type of regex that would show up on an exam. And it's a lot less like, hey, break down this regex, and it's a lot more, this is the identifier regex, so that you can just casually match all your identifiers to a regex, and I don't have to manually define them all. That's what I really mean about like a regex you need to recognize. It's less about, yeah, it helps to understand what you're looking at, but it's not like I'm going to give you complex regexes. It's a tool. Oh, I want to give you a grammar that works for mini programs, like input programs in some form. Programs have identifiers for variable names. I want to use a regex so that I can use whatever variable name I want in my input program, and my grammar does not care. That's just generally speaking the way to want to do it. You don't want to hard code what variable names you're allowed to use. This isn't Fortran. We don't want to do that. So we can use a regex instead. So like, this is the type of thing you need to recognize. Okay? Because yes, we can jam these regexes into BNFs. And that makes BNFs a lot more interesting and a lot more powerful. Because that means that, well, we can just define an identifier as a regex, right? And if it's defined as a regex, then a small number of literal characters defines a vast set of possible valid strings, which makes our grammar just a lot more expansive and a lot more useful. So here are basic grammars as such. A sentence breaks down to a noun phrase and a verb phrase. A noun phrase to an article and noun. This is very similar to the grammar that we saw a few slides ago. The main difference, there's some tweaks, there's no period. We have articles can be a, and, or the. We flesh that out. But the real difference is that nouns and verbs break down into just alphabetic regexes, one or more alphabetic characters. So instead of hard coding specific English words that the noun and verb non-terminals can derive into, it's just a regex. Any combination of just letters is valid. So valid sentences. A person runs a marathon. A bank loses the money. Should that have 1-0? Probably. A key writes and XYZ. Wait a second. That doesn't make any fucking sense. It doesn't have to. This isn't semantics. This isn't meaning. This is structure. This is a structurally valid sentence, this last bullet point down here. You know, we start with a noun phrase starts with an article is and, so we start with and. And then we need, you know, a noun phrase, article and a noun is just any set of letters. Key is a set of letters. The thing we have after that is a verb phrase, which is a verb. A verb is just any set of letters. After the verb phrase, or the verb phrase is a verb, and after the verb it's a noun phrase is an article and a noun, and is a valid article, and then any set of letters is a valid noun. So, and he writes and XYZ. Structurally valid, we have our articles where they need to be, And nominally, key is a noun, writes is a verb, XYZ is another noun, according to the grammar. Those collections of characters match the regexes for noun and verb. But it's meaningless, right? And it's worth reinforcing that BNFs define structure, but they do not define meaning. So this is a structurally valid sentence down here. It matches based on the start symbol and all that, but it doesn't mean anything. We speak English, so we know that, right? When it comes to programming languages, the semantic meaning cannot be intuited. We're going to need a way to define that too. But put a pin in that. That's going to be a little while. We're going to focus on syntactic structure for a bit longer. It's just worth driving home, right? Whereas invalid sentences, my bank loses the money. Did my ass really spell loses two different ways on the same slide? Amazing, iconic, high fucking art right there. Anyway, this is invalid because a sentence breaks down to a noun phrase starts with an article. Articles are a, and, or the. My is not an article, so this is not valid for the grammar, even though this makes sense. Probably not the vibe I want to be putting on the lecture slides, but whatever. What the fuck? Okay. Am I? Okay. So, basically, all I want to show here, this is the program grammar that we used a little while ago to do our big example. Only difference here is expression breaks down to a var, regex var, or just a var. This is something you might show up on a homework. You can look this up. This would not show up on an exam. This is not word, symbol. So this is the set of all symbols. No, I don't quite, strictly speaking, know what the set of all symbols is. I'm assuming it's based off ASCII, but there's, I'm sure, a manual somewhere deep in a dungeon somewhere that formally defines this. But this is basically saying no word characters, just symbol characters. So it's basically saying any valid, just a var, a cluster of symbols, and a var. So nominally, this allows, structurally speaking, any operator to be placed here. We can do a mod B, A and B and C, or B and A. We could do pluses, minuses, equals, equals. We can do whatever we want, so long as they match this regex. Now, this is what I want to leave us with. What if var was defined by, did I write it down? Okay, right, I did. /W and /W. Again, this is stupid regex stuff you don't really need to know. The point is, this is word and not word. So basically, if you have the set of word and the set of not word, without knowing what that defines, we can assume it defines every valid character in the character set. Right? If it's this and not this, we can assume that's all encompassing, right? So a var can be literally anything. Fuck. That breaks the grammar. That breaks the grammar. And that breaks the grammar because if a var can be anything, well, how do we, that includes space characters. And if a var can include spaces, then how do we know if A is a var or A equals B is a var? What's the difference between the two of them? It becomes ambiguous, which is which, right? Because, well, we're kind of implicitly using spaces to separate our terminals. But if a terminal can include a space, then we can't do any derivations. So if I swap this out for a more traditional, just a var is any alphanumeric string, we can do derivations again. This is where we're going to end today. The point to end on is simply that we need to define these regexes so that we have a symbol or a character or a way to keep terminals separate from each other. How do we know we have two separate terminals and not just one big terminal? And that's what we'll pick up on Thursday. So thank you all so much for being here today. Look, we ended lecture mostly wrapped up with a bow for once in like weeks. So yeah, thanks to everybody. If you have any questions about A6, just let me know. Otherwise, I'll see you back here Thursday. Best of luck. Bye, everyone.